in this situation, we have the make before break circuit. When we slide the switch to part A, or spot A, we are in the charging mode of an LR circuit. So under these circumstances, we will start with zero current because we will get a back EMF the moment it's connected, and that back EMF will prevent the flow of current, but that will begin to change almost instantaneously, and we will get a slow progression of increased current until we reach the steady state level. And at the steady state level, the current will be at a maximum. That maximum is determined by the size of the resistor. The time this takes, of course, as you guys have looked at the charging equation, is based also on the size of the resistor and the size of the inductor. So if we consider just like the way the capacitor works, the time is based on how fast it takes for our current to get up to speed. R is in a slightly different position on this one if you looked at the equation, right? You guys have that in front of you from yesterday? This one, the charging equation. There. I don't know if you have in your recollection how this is different from the charging equation for a capacitor. Oops. But for a capacitor, it was very similar. Except R was in the denominator of the fraction, which meant that if R was bigger, it would take longer for the capacitor to charge, which I hope makes good sense, because remember, if R is bigger, current is going to be a smaller value overall, and therefore the trickle of charge getting into the capacitor is going to be slower, and therefore it takes longer to charge. Here, R is in the numerator, which means a larger resistor is going to cause the inductor to charge up sooner. And this is because the max current is less, so it doesn't have as far to go to get fully charged. So that's why it's in a different place here. Does that make sense? If R was smaller, it would take longer to charge up an inductor because the ceiling for the max current is higher. And so it's got farther to go. So that's a subtle difference, but it's worth noting that you don't have either charging equation, on your equation sheet. So having a bit of an understanding of why R is in the place it is probably important. Both L and C are in the denominator because the larger their value, the more energy they can hold. So a larger capacitor will take longer to charge because it can hold more energy. We have to wait till all the energy gets there. A larger inductor will take longer to charge because it's can hold a lot more energy. It will take time for it to get there. So in this circuit, when we're in position A for the switch, we're in the charging side of the circuit. But unlike a capacitor, we can't just take that energy elsewhere. We can't separate the inductor from the circuit and then use its energy at some later time. We will have to use that energy immediately. So unlike a capacitor, which can store energy for later use, an inductor stores energy while the circuit's operating and only while the circuit is operating. So in order to use it to maybe continue to power the resistor, you could slide the switch to B. When you do so, you use a make before break circuit so that you have this transitional moment here, right? Where the current is still being pushed through the inductor, but we are about to break off the battery, but we have a new connection made. And then we proceed to here. So you throw the switch quick, it makes the new circuit before it breaks the old one, and now we can discharge the inductor through the resistor. A make before break switch. Now, this will allow us to do a discharge equation for an LR circuit. I leave that to you because I think it's a good exercise, and treat that like homework problem number 1. I've posted some homework problem with some practice inductor questions. I think there's 6 practices. There's not many, and there's not much inductor stuff on the exam. Try this out though. Develop the inductor discharge equation. You kind of probably know what it's going to look like. If you can see the similarities between this equation and what we had for a capacitor, then you should probably be able to see the similarities between the discharge of an inductor and the discharge of a capacitor. But try it. In this case, though, we assume the inductor has max current already in it. You start from there. Your initial condition is that at time 0, the current is at max. That will be your initial condition. Does that make sense? Okay. I think I would like to talk about an LC circuit today, but I also have a practice FRQ which has an LR circuit practice on it. I'm probably thinking that the LR practice is probably more valuable, but I kind of want to talk about the LC circuit. So, just practicing an LR practice just feels boring to me. But if that's what you guys would prefer to do, I can break that out and hand it out. Or would you like to talk about LC circuits? Because if we talk about LC circuits, we get to talk about a second order differential equation, which I think is kind of cool. So, what's that?
Can we do the FRQ tonight? Okay.
I love you, Gabby. You're awesome. All right, so let's talk about this circuit. An LC circuit begins life as just a charging capacitor. So in this circuit, we're going to charge the capacitor, and then we're just going to create the LC circuit from there. There's other ways to do this, but this is the way we're going to do it. So switch A is closed and stays closed for a very long time so that the capacitor develops a potential difference across it equal to the applied potential difference, the battery. So after a long time, switch A is opened, and now we can begin switch B. Now, when we close switch B after switch A has been opened, so we open switch A, and we close switch B. The moment we close switch B, that is time equals 0. And at that time, the energy is in the capacitor. So we have 1/2 CV squared in the capacitor. Okay? So there's no current in the circuit. All of the potential is currently in the capacitor. Kirchhoff, make a nice little Kirchhoff loop. I want to get this right. So when we do our Kirchhoff loop, we'll have minus the EMF across the capacitor minus the EMF across the inductor equals 0. From yesterday, or from last semester, the potential difference across the capacitor is Q over C. And from the day before yesterday, the potential difference across an inductor is L di dt. And that equals 0. Voltage drops across anything that's not an active battery. I got it wrong a couple months ago when I had to say I was sorry in front of class, but anything that's not an active battery that is actively separating charges is a potential difference, is a potential drop in Kirchhoff's law. So if it was a battery which actively separates charge and adds energy to the system, it would be a positive. If you go from the small line to the big line. Now, we're not going to get very far here, but QC equals L di dt. Not a whole lot there. But remember, I is already dq dt, which means that we can sub in dq dt for I in di dt. So And that's what makes this a second order differential equation. Now, you don't have any tool set for this. There's nothing in calculus that we can do here. And so there is no way to solve this for you guys. However, the first thing you learn in differential equations is a method for solving this. Or at least when I took differential equations, they started here. And I know that it might be funny, but like, how do you begin? It's kind of funny the way you do this. We're going to learn a method to solve this, and it's the most ridiculous method that exists. Let's go ahead and put this in terms of the differential, meaning let's solve this for the differential. And when we do, we get d squared q over dt squared, second derivative of q with respect to t, equals minus q over LC. I'm going to write this a little different, just to separate out the variable from the constants. Now, what this says is, when I take the second derivative of the function for q, I get back the original function and a constant. Right? This is the original function. This is a constant. Can you tell me any function that you know that when you take the derivative, you get back the original function? Sine and cosine, what else? E to the x. These are all functions where if you take the derivative, you get back the original function. We are going to use a process known as guessing to get our answer. And I know you laugh, but that's the first way of doing differential equations. That's what this differential equation tells us. It says, when I take the second derivative, I will have back the function plus a constant. Let's try. Let's say we use the exponential. So we set up the exponential. Now I'm looking here, and I'm noticing what my constant looks like here. I know, let's say AT, and we'll put something here like Q max or something here, because it's got to be Q there. It's got to be something that has charge here. When I take the first derivative of this, I'll get Q times A e to the AT. Right? If I take the second derivative, meaning taking the derivative of this again, I'll get Q A squared e to the AT. You see it? So if I collect the Q and the E part, this is A squared times Q. The second derivative has given me back my original function times a constant. So I guessed at a solution. I tried it by taking the derivative twice, and I have something that looks similar to what I need. My original function and a constant out front. Yeah?
Yeah, I'm confused on how you get it from the second differential to a squared q.
Okay,
Not where you just drew the arrow, the other equal.
here to here?
No, the q a squared.
Oh, here to here.
Yeah.
If I rewrite this as a squared qm e to the at, do you recognize this as being my original function?
Yes.
So all I did was substitute. Does that make sense? Okay. So the problem is that, if you noticed, this is not exactly what we want. Sorry, I don't know why I erased all that. When I look at this original function here, I have to take the second derivative. And when I take the second derivative, I will get back a constant, my original function, but also this negative sign. I don't have the negative sign here. I could try to modify my function to see if I can get a negative sign. For example, I could put a negative sign up here, because I know that when I take this derivative, that will produce a negative sign here. Right, but when I take the second derivative, I get rid of the negative sign. So so this one failed. I always start with this one because I want to prove to you first that there are options, but right, this one fails. So we guessed clearly wrong. And come on, we knew it was going to be sine or cosine. It's an oscillating function. Sine or cosine makes the most freaking sense. But I wanted to start with something that makes no sense to show you that you can guess at a function and be wrong. It's close.
Wait, what exactly are we guessing? Are we guessing what the original equation is?
Yeah. All we know about the equation is that when we take the second derivative, we get back a constant times the original equation. We're trying to guess at what function would do that. And so our first guess was q e to the at. That was our first guess. This is a function for q with respect to t. Yeah?
So if it has a negative, is it just most likely a sine function?
Well, it can be sine or cosine. And it's not an arbitrary choice which. We have to pick one. So let's try that. Let's consider q could be either one. I'm just going to write big Q and not Q max. So I don't know which of these two functions will work best. And they're not very different from each other. When I take the first derivative, dq dt, the first one's going to be qa cosine at. The other one's going to be minus qa sine at. Take the next derivative. First one's going to be minus qa squared sine at. The other one's going to be minus qa squared cosine at. Both of these are possible answers because both of them do what we want them to do. In both examples, we get back a minus sign, a constant, and the original function. Right? In both equations we do. When we look back, our constant must be 1 over the square root of LC. That has to be our constant. Because in our original function, we look back at what that was, this is what we're seeing is a squared. This is the product of Kirchhoff's laws and applying it to our circuit. Since we're talking about charge, this must be what the capacitor is doing, because only the capacitor stores charge. So this is the charge on the capacitor. So going back to these, we've guessed at a solution. We have two possible contenders that both fit. Which one is the right answer? Got a few people have their hands up. Lawrence.
Would it be cosine? Because no, would it be sine because the charge has to be like it starts off with a charge.
You're right in that we have to apply a boundary condition. Which one of these would show max charge at time 0? Aramis? Cosine. This has to be the function.
That's what I said.
Sine would have no charge on the capacitor at time 0,
My goodness.
but cosine would show max charge at time 0.